A very good morning, respected dignitaries, our Honorable Vice Chancellor, Professor K. Sitaramaravu garu, Dr. 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 Venkat Mohan garu, Senior Principal Scientist, Indian Institute of Chemical Technology, Hyderabad, our Director Academic, Professor Pushpa Chakrapani garu, our Registrar Dr. Professor A.V.R.N. Reddy garu, Senior Professors, heads of the branches, deans, directors, and all the teachers and the staff of the university, and my dear students. We all know that our Indian scientist, physicist, Sir C.V. Raman, Chandrasekhara Venkata Raman, discovered the Raman effect on 28th February in 1928. So in India, in 1987, we are celebrating National Science Day to commemorate the Raman effect every year. So on this occasion, we are gathered here for this program. So on this special occasion, the theme for National Science Day 2024 is Indigenous Technologies for Viksit Bharat. On this particular special occasion, the Faculty of Sciences is organizing the lecture program on technological interventions for sustainability and resilience. So I warm welcome to you all for this program. Now I request our Honorable Vice Chancellor, Professor Sita Ramarao garu, to come on to the dais, who is President of today's program, to occupy the chair. And I request Dr. Venkat Mohan garu, who is chief guest of today's program, to come on to the dais and occupy the chair. And I also request the Director, Academic, Dean, Faculty of Sciences, Professor Pushpa Chakrapani garu, to come on to the dais and occupy the chair. And our beloved Registrar, Professor A.V.R.N. Reddy garu, will join soon. And now I request Dr. Premila to present bouquet to our Vice Chancellor, Professor Sita Ramarao garu. Okay, Secretary.
దానికి పోయి కత్తి మర్చిపోయినట్టున్నది.
నేను వెంటలేదు కదా పక్కన కాబట్టి మర్చిపోయినాను అంతే సార్.
తర్వాత తీసుకోవచ్చు.
Now we request Dr. Vijay Kumar to present bouquet to our chief guest of today's program, Dr. Venkat Mohan garu. Now I request Giri to present a bouquet to our Director Academic, Professor Pushpa Chakrapani garu. Now I request all the dignitaries on the dais for lighting the lamp and grace the occasion. And also comes in. Now I request Professor Sita Ramarao sir to present the function. Thank you for giving me this opportunity.
సభకులకు నమస్కారం. మాట్లాడు. సో
మీరు చెప్తారా? తర్వాత నేను చెప్పండి.
సో నెక్స్ట్ ఐటమ్ ఆఫ్ ది ఎజెండా ఇస్ ఓపెనింగ్ రిమార్క్స్. సభకు నమస్కారం. ఈరోజు సర్ సివి రామన్ జన్మదినం సందర్భంగా ప్రతి సంవత్సరం మనం జాతీయ శాస్త్ర విజ్ఞాన దినోత్సవాన్ని జరుపుకుంటా ఉన్నాం. దాంట్లో భాగంగానే మన యూనివర్సిటీలో కూడా ఈ కార్యక్రమాన్ని చాలా భక్తి శ్రద్ధలతో జరుపుకుంటున్నాం మనం. అయితే ఈసారి మనం రెండు విశేషాలు. ఒకటి ఏమిటంటే మనం ఈ సెమినార్ హాల్ పేరు ప్రొఫెసర్ బ్రహ్మాజీరావు పేరు మీద మార్చుకొని ఆ పేరు మీద ఆ హాల్లో వాళ్ళ ఈ కార్యక్రమాన్ని నిర్వహించుకునేందుకు మనందరం కూడా గర్వపడాలి, సంతోషపడాలి కూడా. అదేవిధంగా ఈనాటి కార్యక్రమానికి ముఖ్య అతిథిగా ప్రధాన వక్తగా ఇచ్చేసినటువంటి ప్రొఫెసర్ వెంకటమోహన్ గారు ఐఐసిటిలో సీనియర్ సైంటిస్ట్ వారు ఈ కార్యక్రమానికి మన ఆహ్వానాన్ని మన్నించినందుకు, ఇక్కడికి వచ్చినందుకు కూడా మనం చాలా సంతోషపడాల్సిన విషయం. కాబట్టి ఈ రెండు కూడా మనకు వాళ్ళ చాలా ముఖ్యమైన విషయాలుగా నేను భావిస్తా ఉన్నా. పోతే వాళ్ళ టాపిక్ ఏమిటంటే టెక్నాలజీ ఇంటర్వెన్షన్స్ ఫర్ సస్టైనబిలిటీ అండ్ రెసిలియన్స్. Resilience is related to economy. Sustainability is also related to economy, society, nature, environment, whatnot, everything. They are both of them are interconnected. కాబట్టి ఈ టెక్నాలజికల్ ఇంటర్వెన్షన్స్ విషయానికి వస్తే మోస్ట్లీ దిస్ ఏరియా ఇస్ అప్లికేషన్ ఆఫ్ సైన్స్ టు సాల్వ్ ది ప్రాబ్లమ్స్ ఆఫ్ సొసైటీ. కాబట్టి ఈ సాంకేతిక విజ్ఞానం ఏదైతే ఉన్నదో ఇది సైన్స్ యొక్క అక్యురసీని, దాని అన్వయించడం ద్వారా సమాజంలో ఉన్న రకరకాల సమస్యలను పరిష్కరించే విధంగా టెక్నాలజీ మనకు ఉపయోగపడుతుంది. కాబట్టి సైన్స్కు టెక్నాలజీ కంటే కూడా లార్జర్ క్వశ్చన్స్ ఉన్నాయి. అది మనం అర్థం చేసుకోవాల్సిన విషయం. కాబట్టి సైన్స్ ఈజ్ బేసిక్, పునాది లాంటిది. ఇట్ ఇస్ లైక్ ఎ బేస్ ఫర్ ది టెక్నాలజీ. సైన్స్ విషయానికి వచ్చే వరకు నేను సైన్స్ విద్యార్థిని కానప్పటికీ ఇంటర్మీడియట్లో మాత్రం సైన్స్ చదువుకున్నా. తర్వాత ఇక మనకి ఉండబెట్టట్లేదని భయపడి మళ్ళీ ఆర్ట్స్, సోషల్ సైన్స్కు షిఫ్ట్ కావడం జరిగింది. అయితే ఈ సోషల్ సైన్సెస్ విద్యార్థిగా, అంతేకాకుండా సైన్స్ పట్ల ఉన్న ఆసక్తి, ఉత్సాహం, ఏదో కొంత తెలుసుకోవాలి అనే ఒక ఉత్సుకత, జిజ్ఞాస ఉండడం వల్ల ఈ పాపులర్ సైన్స్ కింద దానికి సంబంధించిన సాహిత్యాన్ని చదివే అలవాటు కూడా ఉన్నది నాకు. కాబట్టి దాన్ని కనుక మనం లార్జర్గా దృష్టిలో పెట్టుకుంటే సైన్స్ పట్ల, సైంటిస్టుల పట్ల నాకు కూడా కొన్ని అభిప్రాయాలు, తర్వాత కొన్ని సందేహాలు కూడా ఉన్నాయి. ఈ సందేహాల్ని అభిప్రాయాల్ని క్లుప్తంగా మీతో పంచుకోవడానికి ప్రయత్నం చేస్తాను. ఏమిటి అంటే 2-3 క్వశ్చన్స్ నాకు, అంటే జస్ట్ 2 or 3 ఇంపార్టెంట్ ఏరియాస్ జస్ట్ ఐ వాంటెడ్ టు టచ్ అపాన్. ఏమిటి అంటే, ఒకటి, మన ముందున్న ప్రధానమైన విషయం ఏమిటంటే సైన్స్ను, సైంటిఫిక్ టెంపర్ను, శాస్త్ర విజ్ఞానాన్ని హౌ టు పాపులరైజ్ అమాంగ్ ది పబ్లిక్. దిస్ ఈజ్ వెరీ బిగ్ ఛాలెంజ్ బిఫోర్ అస్. మొదటి నుంచి మాట చెప్తా ఉన్నా. అందుకోసం పాపులర్ సైన్స్ మూవ్మెంట్స్ కూడా వచ్చినాయి. మీకు దానికి బెస్ట్ ఎగ్జాంపుల్గా మనకు 1940s జేడి బెర్నల్, హూ రోట్ సైన్స్ ఇన్ ఇట్స్ హిస్టరీ అని, ఆయన ఈజ్ ఏ ఫిజిక్స్ సైన్స్, ఏ ఫిజిక్సిస్ట్ ఆయన పుస్తకాలు రాసిండు. మన ఇండియాలో కూడా 1930s 40s దేవి ప్రసాద్ చటోపాధ్యాయ ఆయన ఒక ఫిలాసఫర్ ఉన్నాడు, తత్వవేత్త. ఆయన కూడా భారతదేశంలోని ఈ వేదాంతం, భౌతికవాదం, దాని సైన్స్, దాని ఇంపాక్ట్ ఆన్ సైన్స్, వీటి మీద కూడా సైన్స్ హిస్టరీ మీద, హిస్టరీ ఆఫ్ సైన్స్ మీద 2-3 వాల్యూమ్స్ కూడా ఆయన కూడా రాయడం జరిగింది. కాబట్టి వీటి అన్నిటి యొక్క ముఖ్య ఉద్దేశం ఏమిటంటే సైన్స్ను మనం సామాన్య ప్రజానిలోకి తీసుకుపోయి వాళ్ళలో ఉన్నటువంటి కొన్ని మూఢ విశ్వాసాలని తొలగించాల్సిన ప్రయత్నం అనేది చేయాలి. అది చాలా రోజులు జరుగుతూ ఉన్నది. దానికి ఇంకా మనం దాన్ని వేగవంతం చేయాల్సిన బాధ్యత కూడా మన సైంటిస్టుల మీద ఉన్నదని నా అభిప్రాయం. ఎందుకంటే చాలా రకాలు మనం ఇప్పుడు ముఖ్యంగా ఆరోగ్యానికి సంబంధించిన విషయానికి వస్తే, హెల్త్ ప్రాబ్లమ్స్కి వస్తే టీకాలు వేసుకోవాలంటే భయపడేది మనం. ఎందుకంటే మళ్ళీ ఈ మసూచికం లాంటివి వస్తే ఇప్పుడు అది నిర్మూలింపబడదు. ఒక రకంగా చూస్తాం. అంటే టీకా వేసుకోవడానికి కూడా భయపడే, అక్కర్లేదు, పెండ రాసుకుంటూ పోతుంది అని కూడా మనకు చెప్పిన ఉదాహరణలు ఉన్నాయి ఊళ్ళగా. ఇక కొందరైతే టీకా తీసుకోగానే ఇది చాలా ప్రమాదం కాబట్టి ఈ కడుగు దీన్ని పెట్టి కడుగని కూడా కడుక్కుంటున్నారు. అంటే నేను ఇటువంటి కొన్ని ఆరోగ్యం పట్ల ప్రజలకు చాలా రకాలైన అభిప్రాయాలు, అంధవిశ్వాసాలు ఉన్నాయి. వాటిని మనం తొలగించాలి. వాళ్ళ లోపల ఒక సైన్స్ పట్ల ఆసక్తి, సైన్స్ ద్వారా మనకు చాలా లాభాలు జరుగుతాయి మనం అనే ఒక విషయాన్ని మనం వాళ్లకు, అంటే నిజంగా మరి వాళ్ళ లోపల లేదా అంటే ఉన్నది, ప్రజల్లో కూడా మనకు సైంటిఫిక్ దృష్టి ఉన్నది. దాన్ని మనం దాన్ని బయటికి ఎట్లా తీసుకురావాలి, దాన్ని ఎట్లా స్ట్రెంథెన్ చేయాలి, ఇది కూడా ఒక, అంటే చిన్న పిల్లల స్థాయి నుండే సైన్స్ పట్ల ఆసక్తిని, జిజ్ఞాసను కలిగించే విధంగా ఈ పాపులర్ సైన్స్ మూమెంట్స్ కానీ, పాపులర్ సైన్స్ లిటరేచర్ కానీ అభివృద్ధి చేసి ప్రజల్లోకి తీసుకుపోవాల్సిన అవసరం ఉన్నది అనేది ఒక అభిప్రాయం. రెండో విషయానికి వస్తే, సైంటిస్టులకే బుర్రలు బాగా కొట్టుకునే సమస్యలు ఉన్నాయి. వాళ్ళకు కూడా అర్థమవుతుంది చాలా విషయాలు, కొన్ని అర్థం కాని సమస్యల్ని. దేర్ ఇస్ ఎ సేయింగ్, ఏమిటి అంటే వేర్ సైన్స్ ఎండ్స్ ఫిలాసఫీ బిగిన్స్ అని. మనది ఎంతవరకు కరెక్టో నాకు కూడా తెలియదు. కానీ ఎందుకు అంటే, ఫర్ ఎగ్జాంపుల్ ఖగోళ శాస్త్ర సంబంధమైన విషయాలకు వచ్చే వరకు, సృష్టి రహస్యానికి వచ్చే వరకు ఇప్పటికీ కూడా సైంటిస్టులకు కూడా అర్థం కాని సమస్యలు చాలా ఉన్నాయి. మీకు బెస్ట్ ఎగ్జాంపుల్ ఏంటంటే, ఇప్పుడు మన స్విట్జర్లాండ్, ఫ్రాన్స్ సరిహద్దుల్లో కండక్ట్ చేస్తున్నట్టు LHC ప్రయోగం చాలా పెద్ద బిలియన్స్ ఆఫ్ డాలర్స్ ఖర్చు పెడుతున్నాడు దాంట్లో. ఎందుకంటే సృష్టి, ఇప్పుడు మనం ఏమనుకుంటున్నాం, 15 బిలియన్ల సంవత్సరాల క్రితం ఈ సృష్టి బిగ్ బ్యాంగ్ థియరీ తోటి వచ్చింది, బయటకు వచ్చింది. మరి అప్పుడు రాకముందు ఏముండే, అది ఎట్లా వచ్చింది అనేది ఇప్పటికీ సైంటిస్టులు కూడా చెప్పలేకపోతున్నారు. కాబట్టి మరి అటువంటి దాన్ని మనం కలిగించాలి, ఒక దానికి అవసరమైన జిజ్ఞాస కలిగించాలంటే ఇటువంటి టెస్టులు చాలా పెడుతున్నాం. అవన్నీ ఇమీడియట్గా మనకు అప్లికేషన్ సైడ్ పనికిరావు కావచ్చు, కానీ సైన్స్ జ్ఞానానికి ఉన్న పరిధిని, సరిహద్దుల్ని చెక్వేసి ఇంకా ముందుకు తీసుకుపోయే, అంటే హొరైజన్స్ ఆఫ్ ది నాలెడ్జ్ ఆఫ్ ది సైన్స్ విల్ బి ఎక్స్పాండ్. అటువంటి విషయాలు కూడా జరుగుతున్నాయి. ది బిగ్గెస్ట్ ఛాలెంజ్ ఏమిటి అంటే పదార్థానికి శక్తికి మధ్యలో జరిగే ఇంటర్ప్లే. దట్ ఈస్ మోస్ట్ క్రూషియల్ క్వశ్చన్. అది సూక్ష్మ ప్రపంచం కావచ్చు, చాలా పెద్ద స్థూల ప్రపంచం కూడా కావచ్చు, విశ్వంలో ఉన్నటువంటి పెద్ద పెద్ద నక్షత్రాలు, తర్వాత ఇవన్నీ కావచ్చు. ఇప్పటి వరకు వాళ్ళు చెప్పేది ఏంటంటే మనం చూస్తున్న విశ్వంలో కేవలం 4% మాత్రమే పదార్థం శక్తి ఉన్నదా, మిగతా 96% అదృశ్య శక్తి. ఇదంతా కూడా దాన్ని ఏమంటాం మనం, ఇట్ ఈస్ డార్క్ మ్యాటర్ అండ్ డార్క్ ఎనర్జీ అనే ప్రపోజిషన్ సిద్ధాంతాలు కూడా ఉన్నాయి. మరి వీటన్నిటిని తీసుకుంటే ఈ ఛాలెంజెస్ను ముందుకు తీసుకుపోవడానికి అవసరమైన పరిశోధనలు మనం ప్రభుత్వాలు కానీ యూనివర్సిటీస్ కానీ వాటిని ఇంకా ముందుకు తీసుకుపోవాల్సిన అవసరం ఉంది. ఇక మూడో క్వశ్చన్ నాకు ఇది నాకు ఎంతవరకు కరెక్ట్ నాకే తెలియదు, నేను కూడా దీని మీద ఆలోచిస్తున్నాను. ఏమిటి అంటే ఈ స్పిరిచువాలిటీకి సైన్స్కి మధ్యలో ఉన్న మ్యాచ్ చేయొచ్చా? ఎందుకంటే ఇది చాలా వెరీ ఇంపార్టెంట్ సీరియస్ క్వశ్చన్. ఎందుకంటే ఇది నేను చాలాసార్లు చెప్పిన, నేను అనిల్ విష్ణు మొహరీర్ అనే ఒక శాస్త్రవేత్త ఉన్నారు. వారు మన ఇండియన్ కౌన్సిల్ ఆఫ్ అగ్రికల్చర్ రీసెర్చ్లో భౌతిక శాస్త్రవేత్త. ఆయన కూడా మేము పిలవాలని చాలా రోజు ప్రయత్నం చేస్తున్నాం. దీన్ని కూడా పిలవాలనుకున్నాం కానీ వారు రాలేకపోయారు. ఎప్పుడో ఒకసారి పిలుస్తున్నారు ఆయనను కూడా. వారు చాలా మంచి వ్యాసాలు రాస్తున్నారు, ఈ మధ్యలో పుస్తకాలు ఇట్లా రాస్తా ఉన్నాడు ఆయన కూడా. ఇప్పుడు మహాప్రాకృతిక సిద్ధాంతం, ఇప్పుడు ఆధ్యాత్మికత అంటే ఇప్పుడు ఆత్మ మనస్సు, బుద్ధిజం ఏమన్నది బౌద్ధులంతా మనస్సు అన్నారు, వేదాంతవాదులు ఏమన్నారు ఆత్మ అన్నారు, బ్రహ్మ పదార్థం అన్నారు. అంతే తేడా. ఆత్మస్థానంలో మనసు వచ్చింది, ఇక ఆత్మకు సూపర్ పరమాత్మ ఉన్నది అనేది థియరీ. సరిగా వాళ్ళు ఆ కొట్లాడి నడుస్తూ ఉన్నది. కానీ మనకు దానికంటే ముఖ్యం ఈ ఆధ్యాత్మికత అంటే ఈ రిలీజియన్, పూజలు, గుళ్ళు, గోపురాలు కాదు. అది కాసేపు మర్చిపోలేదు. అది రెగ్యులర్ రొటీన్ లైఫ్. అది దట్ ఈస్ నాట్ బాదర్ అబౌట్ ఇట్. ఎవరి నమ్మకాలు వాళ్ళే, ఎవరి విశ్వాసాలు వాళ్ళే, ఎవరి పూజలు వాడిని, ఎవడు భజన చేస్తాడు, ఎవడు ప్రార్థన చేస్తాడు, ఇంకోడు మౌనంగా కూర్చొని ధ్యానం చేసుకుంటాడు. దట్ ఈస్ నాట్ బిగ్ థింగ్. స్పిరిచువాలిటీ అంటే వసుదైక కుటుంబం. ఈ వసుదైక కుటుంబానికి సంబంధించిన ఒక మహాప్రాకృతిక సిద్ధాంతంలో ఈ సైన్స్ను స్పిరిచువాలిటీని కలపవచ్చా? దీని మీద కూడా చాలా సీరియస్గా పరిశోధనలు జరుగుతూ ఉన్నాయి. మా ఆయన ఎవరండి, స్టీఫెన్ హాకిన్స్. ఈ టైం థియరీ అవన్నీ కూడా చెప్పింది కదా ఆయన వాళ్ళంతా ఏమంటారంటే ఈ ఎలక్ట్రిసిటీ ప్రయోగం వచ్చిన దాన్ని దైవకణం అని పేరు పెట్టింది. దాన్ని అది ఏమో తెలియదు, ఇంకేదన్నా కణమా పాతికిల్ల, అవి మనకేం తెలియదు దాని సంగతి ఏంటో పూర్తిగా. కానీ మరి ఇటువంటి ఆధ్యాత్మికతకు మరి సైన్స్కు ఒక బ్రిడ్జ్ అనేది, అంటే పూర్తిగా భౌతికవాదం మంచిది కాదు, పూర్తిగా స్పిరిచువలిజం కూడా పనికిరానికి వచ్చాయి. రెండు కూడా దెర్ షుడ్ బి ఏ బ్యాలెన్స్ బిట్వీన్ ది స్పిరిచువాలిటీ అండ్ సైన్స్. అప్పుడే మనకు వస్తుంది. మరి ఇప్పుడు లేటెస్ట్గా జరుగుతున్నటువంటి జన్యుశాస్త్ర పరిశోధనలు కూడా, పాపులేషన్ జెనెటిక్స్ మీ అందరికీ తెలుసు. మన CCMB వాళ్ళు కూడా, ఇక్కడ సైంటిస్టులు కూడా కొంత ఈ దాని మీద డిబేట్లో ఎంటర్ అయినరు. కొన్ని తప్పు రైట్ అని. ఎవరైనా లాల్జీ సింగ్ అండ్ తంగరాజ వాళ్ళిద్దరు కూడా ఈ డేవిడ్ రైట్ లాంటి జెనెటికల్ సైంటిస్టులతోటి వాద ప్రతివాదాలకు దిగిన చరిత్ర కూడా మన హైదరాబాద్కు, CCMBకి, తెలంగాణకు ఉన్నది. చాలా గర్వం. వీ హ్యావ్ టు ఫీల్ వెరీ ప్రౌడ్ ఆఫ్ ఇట్. కాబట్టి మరి అటువంటి ఈ వసుదైక కుటుంబం, మరి జన్యుశాస్త్ర పరిశోధనలు కనుక తీసుకుంటే ఈ చాలా మన విశ్వాసాలన్నీ మారిపోతాయి, చాలా మారిపోతాయి. ఇవన్నీ మనం ఇవి కొట్టాడుతాం అన్ని చిన్న చిన్న విషయాల మీద, చాలా మారిపోతుంది. అందుకోసం ఈ మధ్యలో వచ్చిన లేటెస్ట్ పుస్తకం ఒకటి ఉన్నది. జన్యుశాస్త్ర పరిశోధనలో వచ్చినటువంటి ఆధారాల దృష్టిలో పెట్టుకొని ఈ వలసలు, నానా జన్యువులు, అనేక వర్ణాలు, అనంతమైన వలసల్లో ఇవి మన మూలాలు అనే పుస్తకం. ఎవరు కల్లూరి భాస్కరం గారు ఈ మధ్యనే రాసిండు. చాలా పెద్ద ఎత్తున దాని మీద చాలా మంచి చర్చ జరుగుతూ ఉంది. కాబట్టి మరి వీటన్నిటి కనుక మనం కలిపి ఆలోచిస్తే దేర్ షుడ్ నాట్ బి మచ్ క్లాష్ బిట్వీన్ ది సైన్స్ అండ్ స్పిరిచువాలిటీ. కాబట్టి స్పిరిచువాలిటీ, సైన్స్ షుడ్ గో టుగెదర్ ఇన్ వ్యూ ఆఫ్ ది సొసైటీస్ వెల్ఫేర్, విశ్వమానవ విశ్వజనీయమైన విశ్వమానవ, తర్వాత మానవీయమైన సమాజం ప్రపంచం మొత్తం మీద, అంటే యుద్ధాలు, హింస ఇటువంటి అన్నిటి లేనటువంటి ఒక ప్రపంచ శాంతి, మంచి సమాజం, ఉన్నతమైన సమాజాన్ని నిర్మించడం కోసం పూర్తిగా భౌతికవాదానికి, పూర్తిగా భావవాదానికి, ఒక రెండు ఎక్స్ట్రీమ్లకు మనం పడిపోకుండా ఒక నైతిక భౌతికవాదాన్ని, బుద్ధిజం చెప్పినట్టు ఇటువంటి ఒక సిద్ధాంతాన్ని మనం రూపొందించాలంటే ఈ సైన్స్కును స్పిరిచువాలిటీకి మధ్యలో ఎక్కడో దేర్ మస్ట్ బి సమ్ కామన్ ఫౌండేషన్. ఈ కామన్ ఫౌండేషన్ తీసుకురావడానికి మన సైంటిస్టులకు, తర్వాత వాళ్ళతో పాటు ఈ ఫిలాసఫర్స్, సోషల్ సైంటిస్టులు, ఈ చరిత్రకారులు వీళ్ళందరికీ కూడా కలిసి పనిచేస్తేనే సాధ్యమవుతుంది. ఇంటర్ డిసిప్లినరీ వర్క్ అయితేనే అవుతుంది. ఎవరికి వాటి పని తీసుకుంటూ పోతే అంతే. ఈ రెండు కలవవు ఎప్పుడు. మనం ఎంత దూరం ఎందుకు టెక్నాలజీని ఎడ్యుకేషన్ మ్యాచ్ చేసినా, ఆన్లైన్ లెర్నింగ్ ఓడియల్ వచ్చిందా, మరి ఇట్లా ఇది కూడా ఎందుకు రాదు, వస్తుంది కావచ్చు, వచ్చే అవకాశాలు ఉన్నాయి. కాబట్టి దీస్ ఆర్ మై జనరల్ లేమెన్స్ అబ్జర్వేషన్స్ అబౌట్ ది science and its relevance to society. Thank you very much for hearing me patiently. Now, I request Professor Pushpa Chakrapani to introduce about the program and also about the chief guest of the day. Thank you very much. Thank you once again. Yes.
Thank you very much for the opening remarks on this National Science Day. We have posed many questions which are to be debated and discussed on philosophical foundations. Very good morning to all of you. Respected Vice Chancellor, Professor Sita Ramarao Garu, President of today's function, Dr. S. Venkata Mohan Garu, Principal Scientist, IICT Hyderabad, and my dear friends, colleagues, faculty of science, staff, teaching and non-teaching fraternity, and my dear students, very good morning to all of you. And also I welcome you all for this National Science Day once again. And I extend my warm greetings to all of you on this auspicious occasion of National Science Day. At the outset, I am very grateful to our chief guest, Dr. V. Venkata Mohan Garu, for accepting our invitation and came here to deliver a lecture on technological interventions for sustainability and resilience. So thank you so much. And as Dr. Sridevi said in her introductory remarks, we all know that Science Day we are celebrating on February 28th to commemorate the discovery of the Raman effect by Sir C.V. Raman in 1928, and where he received the Nobel Prize also. And for this, every year the nation has come up with a certain theme on National Science Day, and it was decided as Science for Sustainability. And recently, our Union Minister has declared it as indigenous technologies for Viksit Bharat. So today we are gathered here to celebrate the remarkable achievements in the field of science and technology that have transformed our nation. Sir, every year the Faculty of Science celebrates the National Science Day, and let me tell you the very recent scientists who have come to our university to deliver this lecture. We invite the distinguished scientists across the country on this Science Day. So in 2023, Dr. Vithal Telvi, a distinguished scientist from Goa, who is the founder of Farthest Galaxies, came and he spoke on exploration from deep ocean to deep space. In 22, Sri P. Raghuveer, IFS officer, retired from the Forest Department, and he delivered a lecture on ensuring a sustainable future. And Dr. Manorama Sunkara, who is also a senior scientist from IICT, also she delivered a lecture on women in science. And now we have with us Dr. Venkata Mohan delivering a lecture on technological intervention for sustainability and resilience in 2024. So as science people, we all know that science is not just a collection of facts. It is a way of life, way of thinking, the process of exploration, experimentation, and discovery. So it empowers us to unravel the mysteries of the universe, find solutions, as our Vice Chancellor told. So it has given, so we get the solutions from the sciences to complex problems and also improves the quality of our life. So realizing this in true sense, and also the fact that the National Science Day is not just celebration of the day, it is also we feel the reflection of the day and to get inspiration from the past achievements and scientific advancements. So in order to celebrate the spirit of science and inquiry of knowledge and the pursuit of the knowledge, the Faculty of Science, Dr. B.R. Ambedkar Open University, organizes not only the Science Day, sir, to inculcate the scientific temper among our students. We also organize some of the awareness as well as extension programs also for the science students in our university. So some of the programs what we have conducted so far is conservation of biodiversity, science and technology for sustainable development, cancer awareness and screening program, biodiversity, human responsibility, biology to biotechnology, innovations and challenges in chemical sciences, 21st century, awareness program on organ donation, gender equality in science and technology today for sustainable tomorrow, nanocellulose, a sustainable replacement for plastics and more, and recent trends in cancer, biology, advances in physics and cyber security, so on. Sir, you know, Ambedkar Open University is the first open university introduced science programs to distance education at undergraduate level in 1982. And we have introduced PG programs also since 2008 onwards. And now eventually we have introduced the programs, research programs, which leading to MPhil and PhD degrees also. Sir, I'm very happy and proud to say that the students are across the country for our post-graduation studies. And in this occasion, I really thank our Vice Chancellor for his thoughtfulness to name this e-classroom with the name of Professor S. Brahmoji Rao, who was the founder person in the university and who strived for introducing the science programs in our university. Sir, always the university feels that investing in science education and research is an investment in the future prosperity and well-being of our nation too. So therefore, it is imperative that we encourage our youth to pursue careers in science and inspire them become the innovators and problem solvers of tomorrow. Sir, on this occasion, let us express our gratitude to the scientific community for their unwavering commitment to advancing knowledge and technological interventions and pushing the boundaries of human understanding. Let us also pledge to support and nurture the next generation of scientists, providing them with the tools and technologies and reduces the required resources they need to make groundbreaking discoveries. So on this National Science Day, I wish that may the flame of curiosity continues to burn bright in hearts and minds of every citizen and driving us towards a future that is sustainable, inclusive, and prosperous. Thank you, one and all. So this is all brief about the programs which the university has taken up so far, and also a brief introduction of our university science programs. And let me take the opportunity and to introduce our chief guest today, Dr. S. Venkat Mohan Garu, who is delivering a lecture on this National Science Day. Sir, it is my privilege to introduce you, sir. Dr. S. Venkat Mohan is working as a scientist at CSR Indian Institute of Chemical Technology, Hyderabad since 1998. He has done his BTech Civil Engineering, MTech Environmental Engineering, and PhD from Sri Venkateswara University, Tirupati. Dr. Mohan was visiting professor at Toyota University in 2005, Alexander von Humboldt Fellow at Technical University of Munich, Germany during 2001 to 2002, and Kyung-hee International Fellow, South Korea in 2018. Dr. Mohan research majorly intends to understand and respond to the human-induced environmental changes in the framework of sustainability in the interface of environment and bioengineering. His research focuses on designing self-sustainable systems and technologies through a nexus approach enabling production of low carbon energy, chemicals, materials, adopting regenerative resources management. His research interests are in the fields of acidogenesis and bioelectrogenesis, photosynthesis and fermentation, circular bioeconomy, waste remediation, and sustainable engineering. He also works on various industrial, societal, and consultancy projects. Dr. Mohan authored more than 440 research articles, 65 chapters for books, edited 5 books, and he got 14 patents. His publications and more than 32,000 citations with a high index of 97 in Google Scholar. He has guided 38 PhDs, 2 MPhils, and more than 100 MTech and BTech and MSc students also. Dr. Mohan is a recipient of the coveted Shanti Swarup Bhatnagar Prize for the year 2014 in Engineering Science from the Government of India. He also received several awards and honors, which include Abdul Kalam Technology Innovation National Fellow by DST, SERB, and INAE in 2022. Golden Peacock Eco Innovation Award for the year 2022 by Institute of Directors. Dr. C.V. Raman Award 2020 by Government of Andhra Pradesh. DBT Tata Innovation Fellow 2018 by Department of Biotechnology. Vasvik Award, is it right, sir? Vasvik Award for the year 2018 in the category of Environmental Science and Technology by Vividhalaksi. What is this, sir? Ayodhika Samshodhan Vikas Kendra. Most outstanding researcher in the field of environmental science in India, 2018 by Career 360. National Bioscience Award 2012 by Department of Biotechnology. Sir IGCW 2017 for Biohydrogen Technology from DST, SERB. Environmental Engineering Design Award 2017 by National Design and Research Forum of Institute of Engineers, India 2017. Prosper.net Scopus Young Researcher Award in Sustainable Development 2010 under Energy category by United Nations, University and elsewhere. NASA Scopus Young Scientist Award 2010 in Earth, Oceanography and Environmental Sciences by NASA and elsewhere, and Nawab Jung Young Bahadur Memorial Prize 1994 by the Institution of Engineers, etc. So many are there to read. Dr. Mohan is elected Fellow of National Academy of Engineering, Telangana and Andhra Pradesh Academy of Sciences, Biotech Research Society of India, International Forum on Industrial Bioprocesses, Institution of Engineers, International Society for Energy, Environment and Sustainability, etc. Dr. Mohan is serving on the editorial board of journals like Bioresources Technology, Transactions of the Indian National Academy of Engineering, Environmental Technology, Material Circular Economy, etc. So there is a lot to read, but I limit to this only. Sir, thank you so much for accepting an invitation, came here to deliver a lecture. We are very honored to have you on this National Science Day, sir. Thank you once again. I welcome you once again. Thank you one and all.
Since our registrar is not there here, now I request our chief guest, Dr. S. Venkata Mohan, to deliver his lecture. Repeat here.
That will be easy now.
Thank you, madam, for nice introduction. Honorable Vice Chancellor, Dean Dr. Pushpa, madam, and Dr. Madhusudhan Reddy garu, Professor Madhusudhan Reddy garu, other delegates, faculty, as well as students. It's my honor today to be here to speak on this Science Day occasion, particularly it is named after Sri. So I thank University for giving me this wonderful opportunity to speak something on sustainability and resilience, which is very important in the present context. So National Science Day, but I would like to say 20th of February, the first paper, the paper which got Nobel Prize was published in Indian Journal of Physics. This gained Nobel Prize in 1930. This was published in 1928 on the same day, 28th of February. So that's why National Science Day is being generated and celebrated on 28th February. So this year's theme, as already Madam and others have spoken, indigenous technologies for Vikasit Bharat. So Professor Madhusudhan Reddy garu told me to speak on technology. So I try to look into environment because I am working on environment as well as resilience. So what we are doing in technological interventions to address the climate change, I try to put in this presentation and briefly discuss. So I am from Indian University of Chemical Technology. Our department works on environment, basically looks into all the waste which is generated from chemical process. We try to address sustainably. So how to treat the wastewater, how to reduce the emissions, what kind of interventions we have to do with life cycle analysis. Those things we do. Apart from that, we also do basic research, applied research. Basic research in the sense, waste is not a waste in our context. Waste is a resource. In this direction, we try to use waste as a resource, either in the form of solid, liquid, or gaseous solutions, and try to convert into some kind of value-added products. Either it may be fuels or it may be chemicals. And for this thing, we try to use biological routes as well as physicochemical routes. This is interdisciplinary research, but specifically related to environment and biotechnology. Some of these technologies I try to present in this during today. So I try to put presentation like this. I would try to discuss on climate change and the linear economy, and why we have to move from linear to circular economy. This I will try to take about 15% of the time. And then I move to wastewater. Waste, why? What can we do with wastewater? So how it is useful to our society. Not only for like resource recovery, it also can act as a proxy to identify some of the diseases which are coming that I will try to discuss. And then look into solid and liquid waste as well as gaseous waste, how we can convert that into value-added products. Try to close with some low-carbon practices that we can do to reduce the climate change. So starting with energy, everybody knows energy, particularly after industrialization, 1950, we increased energy consumption significantly because our GDP is increasing and population also significantly increased from 1850 to present 10 billions. So our energy mix basically about 80% of energy mix is from fossils. So fossils means either from coal or gas or some kind of other resources, which are again, it's a fossil-based thing. So because of fossils, which has been there in Mother Earth, we are trying to convert into energy form that is generating all the pollutants, particularly CO2, that is causing the climate change. So in this direction, we are trying to move to renewable energy, which is not fossil-based, which is sustainable. So throughout the globe, there is a significant increment in increasing the renewable energy in order to reduce the CO2 emissions. So we also have a lot of potential. India also has started looking very seriously on renewable energy. India is one of the largest solar energy based energy production thing. Like we have huge resources, huge things coming from wind power. We are also looking into other, and biomass is one of the important resource which also can generate different forms of energy. So not only for energy, so we depend on fossils like coal or petroleum or natural gas for all our requirements, all our material requirements, whatever we are using right now, plastics or whatever material we depends on fossils. So we can say that ours is a fossil-based economy, a fossil-based linear economy. So without fossils, we cannot survive. So fossils, again, you know that they are finite in nature. And with this consumption pattern, it will not be available for next 20 to 30 years. After 2050, what we will do for our requirement of materials, future generations. So we are using without any kind of reserves, we are using that. So either for energy or for our material requirement, we are dependent on fossils. So because of this, particularly using fossils, so we are generating a lot of greenhouse gas emissions. About 80% is CO2. CO2, why it is very potential is because it survives in air for near to 300 to 1,000 years. So it persists in air. So persistence will accumulate it in atmosphere. So at present, when we look into the global context, about 41.46 gigatons of CO2 every year we are producing, near to 40 gigatons. But India, when we look into India, it's near to 3 gigatons. So look into the other countries. China produce significant amount of greenhouse gas emissions, followed by USA. India comes third with 7% of its thing. So we use, particularly in India, among the 3 gigatons of CO2 equivalent energy, we use mostly for power as well as for transportation, near to 50%, and agriculture about 18%, and the other industry 24%. So these are the major contributors for CO2 because of using of fossils. So industrial sector, as I told, industrial sector 24%. Basically, major industrial contributors are iron, steel, cement, chemical, oil and gas, and coal. These are the major significant contributors of CO2 emissions. So now gigatons of CO2 is accumulating in the atmosphere. To go to net zero emissions, we have to reduce that gigatons of CO2. Otherwise, it will be very difficult for future generations. So other important thing I would like to mention here, this is from GAP Circularity Report, recently published. So among the resources, what we are using, we are only recycling 7% of the resources, even though it has value. So about near to 92% of resources we are sending into landfill. So the finite resources, even though it has use, we are resending it into the landfills, so that we cannot use it. So that is very significant number. So coming to this one, again, I would like to say linear economy. So linear economy means, what is linear economy? We are taking material from Mother Earth and trying to use it. And then after use, we are sending it, even though it has value, into the landfill. So for last 200 years, particularly after industrialization, we are practicing this cradle to grave extractive industrial model. So that is creating significant, all the environmental problems which we are facing, we can attribute to the linear economy. So this is one thing. And another point I would like to mention here, this was published in Nature Journal 2020. So first time in history of global Earth, in August, I think, August of 2020, the first time anthropogenic materials, which the man-made materials, increased the biomass which is available on Earth. Biomass represents the resilience, regeneration capability. So that animal as well as plants and other things that cause it of our man-made material. So for example, about animal biomass is about 4 gigatons, whereas plastics is near to 8 gigatons. So you can see how much increment is there. Trees and shrubs, which is very important for resilience, about 900 gigatons, but whatever building materials we are constructing, we have represented, it's more than 1,000 gigatons. So you can imagine how much we have exceeded the self-regeneration capacity of our Earth. So for comparison's sake, human mass, our mass on Mother Earth, is near to 0.5 to 0.8. Somewhere it is 0.5 and somewhere it is 0.8 gigatons. We are very less in the quantity. So here coming to one more thing I want to mention about planetary boundaries. So how to identify, how to know about the status of Earth, how because of pollution or because of man-made activities, so how it is deteriorating. So there is one Stockholm Resilience Center. They come up with the planetary boundaries, taking into 9 important factors which represent the atmospheric aerosol loading, ocean acidification, nitrate and phosphate, biodiversity, stratification, ozone depletion. These things, these 9 parameters they took and put a safe operating space, which is green one in between. So you can see that in 2022, 5 boundaries, particularly with respect to nitrogen and phosphorus source, biodiversity, crossed the safe operating space. So once it crossed the safe operating space, we cannot come back. So this is very important to be in the safe operating space. We lost a lot of biodiversity, as you know. So to come back, to resilient back our system on that, these things cannot happen, particularly with respect to these 6 boundaries. So this was about 3 boundaries in 2009 when they first started. So this is one of the important parameters people looking to understand the sustainability. So this is the last one I would like to discuss with you. It's Earth overshooting. You might be knowing about this one. It was started in 1971 by Global Footprint Network. So what it says is, so in 1971, 1970, it was 1 Earth Day. So that means January 1st is the Earth Day. So it slowly came down, and particularly in 2021, it raised once because of the less activities we have done to COVID. And then now in 2023, it is August 2. So this represents 1.7 Earth days, particularly in 2022, means we need 1.7 Earth capacity to regenerate back, resilient back whatever activities we are doing. So Earth has to rebound again to be in the state of equilibrium, but we need 1.7 Earth. So with the same phase, if you are going by 2050, we require 2.5 times Earth, which is very difficult to resilient back. But when we go with some practices, sustainable practices, that is what net zero emissions globally it is being anticipated. By 2050, we can reach 1 Earth. So this says about the biophysical capacity of Earth. So this resilience is very much important. Biodiversity loss also, this will be represented here. So we have to change, need to change. Change is inevitable. Again, if we are not going to change, and it's very difficult to sustain the same Earth for future generation. So because population by 2050 will be reaching 10 billions from at present about 8 billions. Indian population about 18%. We require a lot of material. So as we are going with extractive industrial model, the present figures with respect to domestic material consumption per capita, it's about 5 to 27 tons per person per year. 5 is at low economy countries, 27 high economy countries, like they use a lot of materials. By 2050, it will be reaching 8 to 17, but consumption will increase to 180 billion tons from 100 billion tons as per 2021. So these are significant figures, increase in materials. So again, we have a carbon budget. CO2 accumulation is already about 2,400 gigatons by right now, compared with the 1850, 50% increment in accumulation of CO2. So that needs to be reduced carbon footprints to 2 tons per capita carbon footprints. At present, average is 4 tons. And if you live like this today, by 2050, we require 3 times more resources, 50% more fuel, 70% more food, feed and fiber, 50% more water. And adding to this, 70% of population will live in cities. So cities, very concentrated packets, about 70% live there, even though it contributes to significant GDP, 80% GDP. 75% natural resources will be used there and contribute for 70% of global carbon emissions. So these pockets, particularly urban pockets, will become very vulnerable for environmental conflicts and are making more damage to the global health. So we have to go towards something sustainable. Sustainable Development Goal 12, resource consumption and production. Sustainable resource consumption and production is very important to consider here. So for considering this one, just I try to put this figure. At present, we are at 50 gigatons. You can see the figure there. This current policies, we are going with 2.7 degrees to 3.1 degrees centigrade by 2050. So if you go like that, still we'll be producing near to 30 gigatons of greenhouse gas emissions. As per the pledge 2 degree pathway, by 2010, we'll be reaching somewhere net zero. So still we have to go with 1.5 degrees pathway, which can reach by 2050 the net zero emissions. So this is a very critical thing which we needs to be thought of. And there is no plan B or planet B. We have to go with same planet. So we have to repair our planet. This is from Interstellar. Many of might be knowing that they search for different Earth because we already spoiled our Earth beyond repair. So keeping into this, we have to move towards sustainable practices. I would like to say natural-based climate solutions, which are resilient. In sixth assessment report, APR sixth assessment report by IPCC, they also mentioned the anthropogenic activities, what we are doing. We have to move towards adapting nature-based climate solutions as well as circular practices, circular economy practices from linear. So if we go like this way, we can reach the target of 1.5 degrees centigrade. This is the much champion. Circular economy, as I told, this is a very important requirement. Whatever we do, we have to look into sector more. So the economy or other things in a sector mode, like when we produce a product from an industry, we have to design a waste which is coming from that product as a feedstock for next product, so that in making circulation, we can reduce the waste. So we have to keep material as much as possible in circulation without sending into the landfills. That is the basic principle of circular economy, cradle to cradle model. So some examples I will let you know. We are much interested in bioeconomy. I will explain. So when we look into the circular economy, waste is an important component. So in Indian context, we have different kinds of waste, municipal solid waste, huge quantity. Every year it is producing more, generating more. There is no depth of material like fossils. It also contains good energy value as well as nutrients. Good amount of domestic sewage also. Good amount of nutrients, NNP is available here, and sludge, as well as sludge is human fecal sludge, which we are not going to deal because of some issues in India, but to European Union, they are taking it as a very good resource apart from industrial waste. So what we do when waste is there, we have to treat it. So before that, I would like to mention some of the things which speaks about something related to the COVID and antimicrobial resistance. So this is the work which we started in 2000 when COVID started. So we thought, why can't we use wastewater as a media to look into the virus? And like during that time, COVID is very huge, but we cannot look into the whole population. How much we cannot test everybody and look into how much infection is there. But wastewater has a potential. It can look into the community. When we take wastewater at the terminal point where it is entering into effluent sewage treatment plant, we can get the representative of all that community, how much they are affected. So with that idea, we started working on that. And with the support of CCMB, we tried to look into Hyderabad. We took Hyderabad and all sewage treatment plants. We observed there in all the treatment plants, inlet samples during that time has significant amount of viral load. That is not viable viral load, but RNA of that virus. We detected all E genes, N genes, ORF genes, and tried to correlate with the population, how much of city is affected and that particular time of analysis, and we come up the data near to 6 lakhs during that time was affected. So with single sampling, with few samples throughout the city, taking wastewater as a media, we can detect RNA that is related to COVID. So this wastewater has a potential, not only for treatment, but also works as a matrix or a proxy to identify diseases. So this we have done. We also try to identify second wave when it came in February, but at that time we don't know it's a wave, second wave. But after that we realize it. We detect the increment in load also, in COVID loads. And we try to make compartments, depends on the community which is affected, so that if that community is affected more with viral load, then we can delineate, like that we can do. So there are a lot of things we can do with this one. And now we are doing with the National Surveillance Wastewater Surveillance System for Indian government since December 2002. Almost this is the data you can see here. But we observed some peaks during April, May of this last year, and also suddenly in December. So, but we didn't detected all genes. That is for a very short period of time. The middle graph shows from November to some January, we observed the viral load. So another thing which we can look into wastewater is, you know that antimicrobial resistance, which is very potential threat. The more deaths will happen because of antimicrobial resistance in coming days. That is also we can do with wastewater. We can take wastewater from domestic sewage points, terminal points, and separate DNA. And then we can look into the possible genes available, or we can go with sequencing. That we are doing. This is just a snapshot of what we have done for a community, urban community in Hyderabad. So you can see the resistance. We have studied about 128 genes. You can see almost all genes related to first to fifth generation of antibiotics, all kind of antibiotics, there is a resistance. So that means about 128 resistant genes we studied, about 80 resistant genes are available during all seasons. That says that these particular antibiotics, if we use for that community, that will not function. So this will help to guide the medicinal practitioners the appropriate antibiotic that can be given to that community, so that the health management can be effectively done. This thing we are looking at the national level. We have also looked into the pathogens, particularly pathogens which carrying the antimicrobial resistance will have a lot of negative effect. The non-pathogens will not have much thing. Non-pathogen, they carry antimicrobial resistance that can be easily transmitted to the human beings surrounding. So we also look into genetic elements that are possible for horizontal genes transfer when it goes to environment. So these kind of studies also we can do. So coming to how much time is? Another 40 minutes. 10. Another 10 minutes.
Yeah, sure.
No, we can take people.
So coming to the real thing, like wastewater, I told, wastewater needs to be treated. So whatever is there, before releasing it to the environment, we have to treat. So our intention is to go with biological treatment. When we use bacteria, then treatment will be sustainable. So you see the first one, like aerobic process, where we have to give oxygen. The aerobic bacteria will take nitrates and carbon, and then it converts into new cell and new bacteria. We get reduced loads. So this is a common practice we are using. But alternatively, aerobic process there. You might be knowing about gobar gas. No? With oxygen without oxygen, the anaerobic bacteria convert carbon source into methane. So also we can produce other chemicals like hydrogen. We can produce by altering the bacteria, or we can produce electricity, or we can produce biopolymers, or we can produce ethanol, or many chemicals we can produce. So we have to alter the metabolic activity. So we are going with microalgae. The mixotrophic, we can convert nutrients into biomass. So there are huge scope when we look into wastewater. But I would like to show some of the case studies here. So this is very important thing which is required, because whenever there is a liquid biomedical waste which is being sent into the environment, that will have serious consequences, particularly from hospitals, small hospitals, or nursing homes without treatment, if they send wastewater from operation theatre or some kind of high zones, then these virus and bacteria, which are infectious, will return to the environment. So for that, there is a specification, biomedical waste management, where we have to decontaminate with oxidants before sending that wastewater into treatment plant. So we have done a treatment strategy. We have developed a single chamber DTP and dual chamber DTP, where this wastewater will be initially decontaminated with strong oxidants, and then it will be sent into the environment. This is going to come for translation. So again, we try to develop a low-cost treatment strategy, because by wastewater treatment issues, we cannot go with a very complex systems. Maintenance is difficult. So we have designed a system that can operate on gravity and taking into natural activities, like whatever happening in nature. We send environment wastewater. At certain point of time, it will be treated because of plants and microorganisms time. So we try to use that design for effluent treatment, which is coming from laboratory waste, and sewage treatment plant, which is coming from our laboratory. We have developed a low-cost treatment strategy. So the treatment will be different chambers. We try to give different conditions. No chemical addition will be there, only little bit of oxygen. So these kind of systems we can take into consideration. And the terminal point is, again, we can use plants, ecological engineering systems, all kinds of plants, either constructed wetlands or flow-through wetlands. We can treat wastewater very effectively. The final tank here will have fish that shows that treatment has happened, a significant quantity. So these are the different plants which will help us to treat wastewater. So whatever happening in nature, these are the plants which are helping to treat the wastewater, even though we generate without, release without treatment. These are some of the fish which have significant potential to remove the pollutants apart from mosquito larvae. So this case study, I will little bit tell in a detail. So this is one case study, one thing which we are doing with the funding of the Department of Science and Technology. You might be knowing that Pochampalli is a very famous thing in Telangana. So in one of the villages in Siripuram, near to about 80 kilometers from Hyderabad, it's one of the second largest Pochampalli weaving community. About 80% of village having are weaving community, and they depends on this one. So there what they will do, household activity coming from generations. So they do weaving every activity, including dyeing in their backyard, and then send wastewater into the drains. The drains will take domestic sewage as well as dye waste. It goes to low-lying area in the village, and then slowly it penetrates into groundwater and also to agricultural lands, and slowly it will accumulate metals and other things, and it will create problem for future generation. So why we took this problem? There is one cancer colony in Delhi. So Department of Science and Technology, they asked us to take that project. That community, particular community, all the community used to dye denim jeans. So indigo dye is there, very toxic dye. They use hands. Every person, almost 90% in that community are affected with cancer. So, but for us dealing, that is difficult because of language and that. In that context, we took this village because you know that throughout India, there is their own handloom things, clusters, villages like Pochampalli here, like Kanchi, like that. Everywhere they dye as a household activity and release without treatment. That will have long consequences, have a very bad consequence for next generation. This generation may not know, but it accumulates and it goes to something kind of genetic thing. So we took this one, this village, and studied it. Dyeing process we have looked into different dyes, all synthetic dyes and toxic chemicals they are using. And we try to map the village. So to know the drainage pattern. Initially, our idea is to separate the dyeing wash water and the domestic sewage. But that was very difficult because they do in the backyard where their bathing activity is there. So we cannot segregate. So we thought of then going with the combined wastewater. Then we segregated village into different zones based on the pattern of wastewater generated. And then we clustered it and then come up with the wastewater quality, analyze the wastewater quality, quantify the amount of wastewater, dye wastewater, it is generating. And then we selected a treatment plan and studied wastewater and come up with the treatment strategy. This is of our interest. So this is again, we cannot keep the expensive operating effluent treatment plant in a village. It can operate for 6 months, and then afterwards, no operation maintenance will be difficult. So no mechanical parts. We cannot keep mechanical parts. Once it gets repaired, the total system will fail. So we took a design, very simple design. All wastewater will come into a tank, equalization tank. So equalization tank will give a quantity of wastewater with a defined quality. So then it will go to advanced oxidation, where we put a paint kind of thing with the nanomaterials. So it will be exposed to sunlight. We are not using any light, but sunlight only. That will break down the complex molecules a little bit and then go for biological process, aerobic, anoxic, and aerobic process. So aerobic process breakdowns dyes, and then anox process is required to convert it again into nitrates, and then again aerobic process. 3-stage process, all goes with a gravity. There is no pump so far except for blower in aerobic plant. Then the residual thing, any dye molecules or its intermediates will be there. It goes to plants. Initially with anchored plants and submerged plants. Anchored plants will have very good root, which will accumulate metals and then convert the any organic matter into useful things. Like we get the structured water when it goes to plant. Then submerged water, then disinfection. If we do disinfection, the water can be used for non-domestic purpose. Or we are not doing disinfection, it go to so because we are 100%. So there is no, everything goes on gravity. Only solar power will be used for biological treatment, giving oxygen. So this is a complete low maintenance system. So this can function near to 5 days. Once we construct it and then we give to the villages, they can easily manage, no chemical usage. So these kind, if this is successful, the work started last week. And if this is successful, this model can be implemented to different places. That is what our idea. Why dye is significant use throughout India. Everybody know that. So that is our idea with the help of Ministry of Textiles. So now we look into the treatment. So very briefly, I will go to how can we produce fuels or chemicals from wastewater. So this is a chart which I try to put. We can take domestic wastewater, industrial wastewater, solid waste or CO2. By biological process, we can produce the platform chemicals. Whatever we have seen in initial slide, where the petroleum thing is producing chemicals. Now all the chemicals we can produce. These are bio-based chemicals and carbon, low carbon chemicals. So we started working on hydrogen. Now everybody knows that hydrogen is a very clean energy vector. And globally, it is being considered as a potential energy carrier because of its advantage, like it will not emit any emissions. Only water will be emitted. So basically, the process will reduce near 18% of greenhouse gas emissions by 2050. So with when we increase the productivity by 60 times throughout the globe, it has significant impact on decarbonization. So however, the problem is the hydrogen which we are producing should also emit less CO2. So electrolysis if we take, and then we produce using the grid energy 80% non-renewable, it comes near to 20 kg CO2 equivalents per kg of hydrogen production. When it is 2 kg CO2 equivalents per kg of hydrogen production only, we can call hydrogen green, and then it will have positive impact on environment. So that's a challenging thing. So we started quite long time back on production of hydrogens from 2005 using waste. So we have established a pilot plant in 2016, which can produce 50,000 liters of hydrogen. And then we established a waste biorefinery to recover all the resources. This we are at present trying to scale up to 150 kiloliters of hydrogen production. So this data I will not go. This is the pilot plant which we are setting with the funding of DST, complete biorefinery plant, which can produce 150 kiloliters per day of hydrogen, low carbon hydrogen with other chemicals. You can say this refinery will produce not only hydrogen, it can produce acetic acid, nitric acid, biopolymers, and many things it can produce so that overall hydrogen cost will be reduced and CO2 emissions will also be reduced. So we try to do the life cycle analysis. So now, as anybody in any process or product, we have to do life cycle analysis to understand carbon emissions or its impact on environment. Without that, in future, any product or process cannot go into the market. So this is, we try to analyze. Whatever we thought, it will not be sustainable always. We have to have some kind of analysis. So with at present, we are getting near to 5 kg CO2 per equivalent without refinery, but with the refinery, we are getting 1.9 kg CO2 per equivalent with reduced damage categories. So here I would like to mention one thing. So Sar told about Steve Hawkins about the energy, the particle. The particle. That particle we can see in every walks of life, like bacteria produce electrons and protons during its metabolic activity, which is very critical in soil remediation or plant productivity. A microalgae can produce electrons. Yeast also produce electrons during metabolic activity. Plants at root zones where bacteria is there, that is the healthy bacteria which is required. It only generates electrons and try to capture some of the useful products. So everywhere this electron productivity is there when bacteria is there. So when we give some carbon at anaerobic conditions, it will try to convert into electrons and protons. This has given a very significant interest in research community, particularly in 2005 on microbial fuel cells. So same hydrogen production, you keep electrodes, anode and cathode, and separated by proton exchange membrane. The bacteria will produce electrons and protons. Anode will take electrons, and proton passes through proton exchange membrane. Anode passes through the circuit and enter cathode. In presence of oxygen, terminal electron acceptor, it converts into water. So this mobility of electrons is nothing but electricity. So bacteria will, you see the bacterial cell, how it generates electrons and proton. So this will give power. So this has fascinated many initially as a microbial fuel cell, and then it has ventured into different applications. Here I would like to show a couple of applications. So when we want power, it's microbial fuel cell, but it has a very significant potential to treat wastewater. In Siripuram project, DIE project, in middle reactor, biological reactor, we are using electrode assembly to increase the activity of bacteria to convert complex chemicals, that is bioelectrochemical treatment, or we can convert CO2 to chemicals. So some fatty acids or ethanol, bioelectrochemical system. Likewise, this became a platform technology in many places. Few things I will explain, because few things I will explain at the end of the presentation. So coming to the last one, solid waste, very briefly I will go. Here I would like to mention whatever is the solid waste available. If biogenic solid waste is there, basically it is going to landfill right now. Little bit for composting, little more for incineration to energy recovery. But it has potential. Go to digestion or pre-treatment fermentation, we can convert chemicals and other things. But we are wasting those resources. By that way, we reduce greenhouse gas emissions, also increase the energy recovery. So in this direction, here I would like to mention about one of the students from your university. He worked, after doing MSc Environmental Science, he worked in this project. Rana, the Sar knows about him. So he got his fellowship. He has dual degree, one in chemistry, one MSc Environment Science from university. So he worked very, it's one of the very best students, I would like to say. Now he's in Korea. So this is an Indo-UK project. Our aim is to use the biomass coming from sugarcane industry to made into chemicals, platform chemicals. Like, biomass, huge biomass is at present here, burned in North India during particular season because they are not able to manage. But that biomass has significant chemicals in it, like contains cellulose, it contains lignin, contains hemicellulose. So how we are extracting it is very important. The low chemicals. So we try to develop the process for microcrystalline cellulose, which has very significant application in medical industry as well as its composite industry. Come up with the crystalline cellulose by taking cellulose separately with low chemical inputs. This we have patented the production of MCC from different biomass, not only with sugar case, but almost all biomass available in India. So another technology which is emerging. So you know about the fossil material, like fossil crude, which is available in Mother Earth. We take and convert it into petroleum and then refine it into different products. So what is happening there is, billion years back, the biomass, dinosaurs, all other things, it was buried in Mother Earth, and then because of high temperature and pressure, that was converted into biocrude, and we are extracting that. So that is now creating problem. So not doing that, we can stimulate the same conditions in hydrothermal liquefaction, where biomass or bio-waste or microalgae can be put at subcritical conditions for a short period of time by giving pressure. 5 bar pressure at temperature of 300 degrees. With this condition, we get the chemicals. So this is at present energy intensive process, but people are looking into making sustainable aviation fuel. We get 3 fractions: aqueous phase, organic phase, and biochar. So that will have a spectrum of chemicals. You can see biooil composition, C10 to C20 fraction is there, along with the carboxylic acid, others. And the aqueous fraction has significant amount of other chemicals which can be converted. And the gaseous emissions coming from has significant amount of hydrogen. This hydrothermal liquefaction mimic the conditions what has happened in Mother Earth to convert the fossil-based resources. So that we can do within hours in laboratory. But now it's energy-intensive process. Just I want to let you know that this technology is emerging right now. So this is the pilot plant which we have constructed. And in photo, the student is there, Dr. Rana, present. He also worked in this project. So now last one, I would like to say, micro photos, because of lack of time, I will go to the last section. So here I would like to mention about the electrode assembly, the electrons which is coming from bacteria. This was, we published it recently, which was also mentioned in Nature India. We took the advantage of root of bacteria, which is rich in microorganisms, also organic matter. So electron generation will be there. We try to capture by putting electrode at the root jaw and kept cathode above the soil surface like this. So this has created significant impact on productivity. We try to look into 2 plants, Caesaria C3 plants. You can see the difference in plant productivity, leaf size, as well as these things. The more importantly, you can see the CO2 fixation rate. So with the less time, we are able to fix more CO2, that means more oxygen, and also accumulate large amount of carbohydrates. So this is one of the technology which we are significantly looking at present. We are doing with plant, tomato plant, which has lot of potential. So here I will close. Before closing, I would like to mention as an individual how we can contribute to climate change. So this chart shows the recent charts that per capita production of greenhouse gas, carbon footprints. Like India, we are about 2.5 tons of CO2 per year per capita. So, but we are at the 10th place. But you can see other countries, USA, Russia, South Korea, Iran, China, they are far beyond us. USA top seed. So as an individual, we can do a lot of things, but we cannot depend on government for always. So we can reduce 40 to 60% of our footprints by low carbon lifestyle. So basic components, we need energy, we need materials, we need travel, we need food. So among that, when we treat, food contributes to 25 to 30% of carbon emissions. So we can design our lifestyle moving towards low carbon. Like suppose energy is there, we look into energy efficiency. We go with the energy efficiency means we should not waste energy, stop the lights, and go with the renewable energy and replace with LED lights. Our materials, we go for low carbon materials so that carrying capacity of carbon will be reduced. We have to go with recycling or reuse. We have to reduce the material usage, even though not required we purchase, but we should not do that. When we go for travel, you know, hybrid vehicles are coming right now. Probably we have to use public transport, walk, so that we can calculate how much we are reducing. There are calculations. So for food, particularly plant-based food materials has very low impact. Instead of non-vegetarian, we can replace that to certain extent, not full extent. We have to reduce waste, food waste. That is very important waste which is coming into the landfill. So apart from that, our dependability on fossils has to be reduced. We have to advocate sustainability. So we have to advocate, and we have to have a commitment to reduce by this year to next year. We have to reduce at least 5% of CO2 with our lifestyle changes, reduce waste. So like that, we try to list some of the things, how much we are producing each day. Anywhere we can intervene and we can reduce our carbon footprints. So likewise, we also developed a low-cost treatment for individual house or community, very cheap treatment system. We can include in the land itself. So if you are able to reduce carbon load entering into the environment, by that way also we are reducing CO2 emissions. So there are 3 treatment strategies we have developed. I will give the approaches. And we also have worked on keyhole garden. So this is a very important thing. Whatever food waste we are generating in house, with a small area, we can construct a keyhole garden. We can plant whatever things are required for our cooking or our herbs in a small area without much of water. There is a center bin there. Whatever material is coming, we will put in that center bin that will compost itself and give nutrients to the plants. No need to make a compost again. So little bit of rainwater will be sufficient. So this design also I will give. This is a keyhole garden, backyard garden. Particularly it started in Nigeria where they have a lot of food issues during AIDS period because they cannot walk, they cannot get their vegetables. So backyard, they will construct the keyhole means they can enter and put the waste there. That's why that hole is there. They approach the hole and they can they can produce all the plants. So these kind of interventions also significantly reduce the resources. So that is what I would like to say. So we not only depends on government, we have to also commit to reduce some of the CO2 emissions with our practices so that we also can contribute significantly for climate change. That's what I want to tell here. We have a lot of things to do. So I would like to thank my team whose work I have presented here, my students' work, and funding from different funding agency. And thank you very much for your kind attention. I would like to thank Sir for your patient listening and for everyone. Thank you again. Have a time, please come, sir.
Thank you, sir.
So, thank you very much, sir, for a very elaborated presentation on how best we can reduce the carbon footprints, changing our style of life. That is most important and central point to our discussion. Now, we have 2 more items on the agenda. One is conducting felicitations, sir. So, this is our tradition in our university. Whoever comes to our university as a chief guest and speaker, we extend our heartfelt felicitations, kindly accept. And later, vote of thanks by Mr. Basu. Yeah. Before that, felicitations will be granted. I request who is coming? Please come.
Yes, sir.
Hello.
Thank you.
Morning, Manada. We have successfully completed the program. So I would like to extend my heartfelt gratitude for the today's president of the function and our Vice Chancellor of this university, Professor K. Siddharamarav Garu, for sharing his profound insights on science and technology of today's program. And I'd like to convey my special thanks to Dr. Venkat Mohan Garu, Senior Principal Scientist, IICT Hyderabad, for sharing many more things like sustainable renewable energy, biomasses, and importance of fossils, various emissions of CO2, and natural-based climate solutions, and about bioeconomy, and dying process of Siripuram village, and wastage remedies, so many things. Thank you so much, sir. And I would like to thank Professor Pushpa Chakrapani Garu, Director Academic and Dean Faculty of Science, for sharing her message of this program. And I would like to convey all the faculty members of Faculty of Science, Faculty of Social Science, Faculty of Arts, and all other faculties for attending this program. And I would like to thank Director EMRC and Computer in Charge for providing necessary arrangements to this program. And I would like to thank all the participants of this program to make it grand success. And I would like to thanks to all the teaching and non-teaching staff to make this program to grand success. Thank you, Ananda.